Hey there, physical science students. This is Miss Ruark. This is Vodcast 4.2, and we're talking about electric current. So, we just got done talking about heat not too long ago, and we said that heat flows from hot things to cold things. And we call it heat because we can feel a difference in the temperature. And we know that that heat's going to continue to flow from hot to cold as long as there's a difference there in temperatures. Once the temperatures are even, that it's not going to change. There's no heat flowing anymore. And guess what? An electric current is going to work about the same way. The charge is going to keep flowing on an electric current as long as there's a difference in energy. Okay, so example here is a water fountain. This water fountain is going to, the pump in the water fountain pushes water from the bottom to the top of the fountain. And I have drawing all over this, and I didn't even realize it till just now. All right, so the pump pushes water from the bottom to the top of the fountain, and then the water flows back down, and the cycle is repeated. So I know this isn't a water fountain, but it's something to help you see it. The water flows this way and into this pump. Okay? If it was a water fountain, it would have some hose that would lead it back to this reservoir, and it would continue to keep going around and around until it was even. Okay, well here, our pump is going to be our voltage source. It's what's pushing along the water, right? It's pushing along our electrons, because the water would be the electrons. Because for an electrical current, you have to have electrons. Okay, potential difference. So the difference in potential energy or voltage between two ends of a conductor. Okay, this will flow, and it continues until both ends reach a common energy level or a common voltage. Okay, we also know that the bigger the difference in potential energy, gives us a higher voltage. Right? And so what is voltage? Well, it's the amount of electrical energy measured in joules. Energy is joules, right? Big J. This is applied to each charge. And voltage, energy is joules, voltage is measured in volts, V. Right? All right, so current. Current is the flow of electric charge, and current, the letter that designates current, is the letter I. Okay, so the letter I is for current, and it's saying, how fast the electrons are flowing through the conductor. Okay. The flow of electrons is going to be, or the current will be measured in amperes, A-M-P-E-R-E-S, and we use a big letter A to show amperes, or you can say amps. Okay, and so the question is, well, what would be the relationship between I and V? I is current and V is voltage. Okay, well, I is proportional to V. Oops, what does that mean? If it's proportional to V, that means as one goes up, the other goes up. As one goes down, the other goes down. All right, resistance. We're going to put all these, I'm showing you all the pieces to the puzzle, and then we're going to stick them all together. All right, resistance is measured in ohms. Yes, like ohm, okay, in ohms, and that's the funny Greek letter for ohms. Okay, resistance is the electrical equivalent of friction. Okay, and this is the property in a conductor that slows down that current flow. Okay, it's what keeps the current flow from going any faster than it already is. Okay, so what would be the relationship between I and R? Well, I is proportional to 1 over R, which means that they're inversely proportional. So as one goes up, the other goes down. As one goes down, the other goes up. Okay, so in Ohm's law here, it says that if I is proportional to V and I is proportional to 1 over R, then I must be equal to V over R. And we can rearrange that, and we can get a nice linear equation right here that says V is equal to IR. So voltage is equal to current times resistance. And it tells us, this law right here will tell us the relationship between voltage, current, and resistance. What happens if you make one go up? What happens if one goes down? And we'll talk about that in class. All right. So let's look at some examples. How much current is drawn by a lamp that has a resistance of 100 ohms when a voltage of 50 volts is across it? All right, so we've got, let's analyze our question. Okay, so what are we looking for? How much current? That's what we're looking for. How much current, right? And current is I. All right, and then it says is drawn by a lamp. I think we actually were supposed to circle that, weren't we? Yeah, see, I'm slacking. All right, and we label it I. All right, and then is drawn by a lamp that has a resistance of 100 ohms, so we know that that is our resistance, and it has a voltage of 50 V, so we have our voltage. Okay, we're solving for I. We've got R and we've got V. So to solve for I, we take I is equal to V over R, which is equal to 50 over 100, and that gives us 0.5 amps. Let's try another one. What is the resistance of an electric frying pan that draws 12 amps of current when connected to a 120 volt circuit? Okay, so we're looking for resistance. All right, we're looking for resistance. We're going to circle that and label it. All right, we know that it draws 12 amps. 12 amps. What was that? That was current. That was resistance. That was voltage. It was current. Yeah. All right, amps or amperes. All right, and then when it's connected to a 120 volt circuit, so that's going to be our voltage. Okay, if we're looking for R, all we've got to do is get R by itself. So we're going to rearrange the equation. R is equal to V over I. So we put 120 volts over 12 amps and we get 10 ohms. All right, we'll do some more practice with this in class. Okay, so the question is, what causes damage to the body, current or voltage? Oh, this is the time. This is an argued question. People, oh, what happened? People argue this question all the time. All right, so let's see if we can get you smart so you know what the right answer is. Okay, so the damage from shock is the result of current passing through the body. Okay, because our bodies are conductors. Okay, resistance of a human body is 500,000 ohms if the skin is dry, and it's only 100 ohms if it's soaked with salt water. Why salt water? Because salt water has a bunch of electrons in it. Water has electrons, but salt water has a lot of electrons. All right. So, for example, if we had 500,000 ohms for our body resistance and we touched the end of a 12-volt battery, what would be the current that passes through us? Well, I would be equal to 12 volts over 500,000 ohms, and that would give us a current of about 0.000024 amps, which is not a lot. We'll be okay. All right, what if we touch the end of the battery and we are wet with salt water? So our resistance now is 100 ohms, and we touch the end of a 12-volt battery. So to solve for I, we put 12 volts over 100, and we're now putting a current of 0.12 amps through our body. That, my friends, is some serious trouble. All right, so what are the effects of various levels of current? So if we touch a current that's 0.001 amps, we can feel it. If it's 0.005 amps, it's kind of painful. 0.10, we're going to get some involuntary muscle spasms, right? And now you felt them before. You get those little crunch, your muscle kind of jumps a little. 0.015 is a loss of muscle control. And then if we have anything that's 0.070 amps or greater, if it goes through our heart, we could be in some serious trouble. Okay, so what is it that affects us? It's the current. Okay, so direct current versus alternating current. Oh, wait a minute. We need to go back to the resistance because there was something that I didn't talk about with resistance. Okay, and I know you've got a big old space there. So resistance is going to depend on a couple things. It's going to depend on the conductivity. How well does the wire conduct? It's going to depend on the thickness of the wire, and the thicker wires would give better resistance. Okay, the length of the wire, shorter wires are better, and the temperature, colder is better than hot. Okay, so I think I've got that. All right, so now we're at direct current and alternating current. So for direct current, charge is always going to flow in one direction through the circuit, and an example of that would be a battery. Okay, so the pro to that would be steady power source. The con would be, oh, it's hard to send over long distances. Well, in alternating current, the charges alternate the direction in which the flow goes through the circuit. So a normal outlet would be an example of an alternating current. And the pro for that is it's easy to send this current over long distances, but the con is it's kind of an unsteady power source. Okay? All right, so just to get through this quickly, here is an example of a schematic diagram. Okay, and in a schematic diagram, it shows you where the battery source is. Okay, it shows you the flow of the current. It shows you if there are any resistors in here. Okay, and it shows you if there are switches. Okay, a schematic is just pretty much showing you all the basic parts to the circuit. All right, so let's talk about a circuit. Well, there are two types of circuits. You have series circuits and parallel circuits. A series circuit is where they're lined, all the voltages, or the volts are lined up in a line, in a series. Okay, so each device takes a byte out of the available voltage that's left, that's sent through. So let's say that we send through 2 amps here. Well, this one's going to take out 0.5, so there's 1.5 flowing through, and then this one takes out 0.5, so there's 1 flowing through. You see, everyone gets a byte out of it. Okay. In a parallel circuit, each one receives the same amount of voltage. So if we send through 2 volts here, this circuit's going to get 2 volts. Oops. This one's going to get 2, this one's going to get 2, and this one's going to get 2, because they're all getting it fed from the same source. It's coming from the same source here, but this one gets 2, and whatever this takes it down by, it now goes to 1.5. And then it would go down to, let's say, 1.0. I'm just making up numbers here. Okay, so in a series, the available voltage goes down as you pass by each volt, or as you pass by each series. Okay, and I think that's it. All right, so thought this would be funny. I'll see you in class.